Ancient engineers deliberately designed their monuments to warn future generations. This video uncovers the sophisticated systems these master builders used to encode prophecies of societal collapse within stone and water. You will learn to recognize the hidden warnings they left in everything from pyramid alignments to city layouts, revealing a lost science of foresight. How did they calculate civilizational timelines with such precision? And why did they bury their predictions in plain sight? What does their understanding of great cycles tell us about our own time of transformation? What patterns from the past are we still living through today? This worldview of repeating ages was not abstract philosophy, but practical engineering. These master builders translated the rhythm of the cosmos into stone, creating structures that were, in essence, prophetic machines. The Maya, for example, did not simply observe the stars. They built observatories like the Caracol at Chichen Itza with precise window alignments that captured the extreme positions of Venus on the horizon, a planet deeply tied to their narrative of cyclical creation and destruction. Each time Venus reached a certain point in its long dance, it signaled a phase within their great cycle, a moment of potential upheaval. The architecture itself became the needle on a celestial clock, tracking time on a scale almost incomprehensible to the modern mind. This principle appears across the ancient world with stunning consistency. In Cambodia, the vast temple complex of Angkor Wat is laid out as a terrestrial map of the Hindu cosmos, its central towers representing the mythical Mount Meru. The entire structure is aligned with the sun at the spring equinox, and its intricate bas-reliefs depict the great cosmic cycles of creation and dissolution known as the yugas. The builders were not just honoring gods, they were creating a permanent physical record of time's vast turning wheel, a reminder that every age, no matter how glorious, has its appointed season. The real genius of these ancient engineers lies in their grasp of celestial mechanics, particularly the slow, grand wobble of Earth's axis known as precession. This 26,000-year cycle gradually shifts the position of the stars against the sunrise, marking what many cultures called the Great Year. They understood that this slow drift divided time into distinct astrological ages, and they calculated the transition points with astonishing accuracy. The Great Pyramid of Giza, for instance, was once perfectly aligned to the pole star Thuban, a star that held that position only because of precession. Its air shafts point toward specific constellations that were dominant in the sky thousands of years ago, locking in a celestial timestamp. This was a deliberate act, a way of saying, we built this at a specific point in the great cycle, and we are encoding the knowledge of when the next turning will come. This profound temporal awareness is what allowed them to embed their warnings. They were not predicting a single, random catastrophe. They were mapping the recurring patterns of human experience that emerge at the cusp between ages. Their monuments stand as permanent sentinels, designed to activate their message when the stars realigned, and the next great cycle began its turn. So how did they physically build this knowledge into their cities and temples? The principles they used reveal an even deeper layer of intention. These structures were not merely monuments, they were machines built for a conversation with the future. To achieve this, ancient engineers perfected architectural principles that served a dual purpose, creating spaces for immediate use while embedding prophetic messages set to activate centuries later. The Great Pyramid of Giza offers a stunning example. Its narrow air shafts, long a mystery to researchers, are precisely aligned with stars like Thuban and Alnitak. The critical point is that these alignments would have been most accurate not when the pyramid was built, but thousands of years into its future. It is as if the builders calculated the slow precession of the stars and set their stone clock to chime at a specific, distant date. They were sending a signal forward in time, a signal that would only become perfectly clear when the heavens themselves reached the intended position. This same forward-looking genius is etched into the walls of Angkor Wat. Its sprawling bas-reliefs do more than tell ancient myths. They depict scenes that correspond precisely to astronomical events, such as the specific configuration of constellations that would not occur until long after the last stone was laid. The temple itself is a prophetic calendar, its stone narratives waiting for the sky to catch up and complete their story. This method of encoding knowledge was a deliberate response to the fragility of human memory. These engineers understood that empires fall, languages fade, and libraries burn. So they chose the most durable medium they could conceive, stone, and they wrote their messages not in words, but in geometry, alignment, and proportion. The very measurements of these structures often contain mathematical constants and precise astronomical data. This information is immune to translation errors. The ratio of a circle's circumference to its diameter is the same in any language, and the angle of a star's rise is a fact that never changes. They created a universal language built from the fundamental laws of mathematics and physics, ensuring their warnings would be decipherable to any advanced culture that might follow. The immense durability of their construction is itself a profound statement. The choice to build with multi-ton blocks fitted with impossible precision was not just a display of power. It was a practical guarantee. They were building to survive natural disasters, human conflict, and the slow erosion of centuries. This resilience represents a core tenet of their prophecy, a deep-seated belief that civilization, though cyclical, would eventually produce people capable of understanding their message. They were not just predicting an end, they were investing in a new beginning, creating architectural time capsules meant to guide a future age. This ambition to communicate across the abyss of time stands as one of humanity's most profound technological and philosophical achievements. And perhaps their most elegant prophecies were not written in stone at all, but were instead channeled through water. Water is the ultimate measure of a civilization's health. While their stone monuments tracked the slow dance of the heavens, ancient engineers also built prophetic messages into the very flow of water, creating hydraulic systems that doubled as barometers for societal collapse. The Roman aqueducts were far more than just channels for water. Their construction followed precise mathematical ratios that modeled a delicate balance between population size and resource consumption. The engineers calculated the maximum sustainable flow, building in a silent prophecy that when urban growth demanded more than the system could provide, the failure would not be random. It would be a predictable outcome, a direct result of exceeding the ecological limits they had so carefully calculated and embedded in stone and mortar. This was not mere infrastructure, it was a physical algorithm forecasting a future crisis. On the other side of the world, the Khmer Empire at Angkor Thom created an even more responsive system. Their vast network of canals and reservoirs, like the massive West Barre, was engineered with a profound understanding of hydrology. The system was designed to function flawlessly only as long as the surrounding watershed remained healthy. As deforestation in the uplands increased, so would the rate of siltation in the canals. The engineers designed these channels with specific gradients and capacities. When silt built up beyond a certain point, the water flow would begin to falter in predictable ways, first affecting the most distant reservoirs. The system itself would provide a clear, visible signal of environmental stress long before a catastrophic water shortage occurred. It was an early warning system carved into the landscape. Mayan water engineers applied this same foresight to their cities. In regions with seasonal rainfall, they constructed intricate systems of reservoirs and choltons, or underground cisterns, to capture precious rainwater. These were not built for unlimited expansion. The engineers calculated the precise carrying capacity of their land based on water availability. The reservoirs had a maximum capacity, a line that, if consistently reached, indicated the population was pushing beyond what the environment could support. Exceeding this built-in threshold was a silent alarm, signaling that the city was living unsustainably and that hardship was imminent. The most sophisticated examples may come from ancient Sri Lanka. There, engineers created a cascading series of tanks and sluice gates that managed water for agriculture for over 1,000 years. The genius of their design lay in its failure modes. The intricate sluice gates, often called Bisakatuwa, were engineered to respond to specific conditions. If upstream land management failed and soil erosion increased, the sediment load in the water would rise. At a critical point, this sediment would begin to interfere with the precise operation of the gates, causing them to malfunction in a distinct, diagnosable way. The system was designed to break down in a manner that pointed directly to the root cause: severe environmental degradation. These hydraulic networks were more than just feats of engineering. They were physical models of a civilization's relationship with its world, built in prophecies that used the universal language of water and physics to warn future generations. They understood that when the water falters, everything soon follows. This desire to measure and predict extended far beyond the Earth, reaching for the stars themselves. These observatories were not passive structures, they were active instruments in a grand celestial forecast. The caracol at Chichen Itza stands as a testament to this purpose, its strange, spiraling tower punctured by narrow windows that seem to aimlessly peer at the horizon. Yet these openings were precisely calibrated to frame the extreme positions of Venus in its 8-year cycle. For the Maya, Venus was not just a bright star. It was a deity, a harbinger whose specific celestial movements signaled periods of potential upheaval, war, or the end of a smaller cycle within their long-count calendar. The building itself was a mechanical computer, its stone components processing the movements of the cosmos to output a prophetic reading of time. This same principle of monumental forecasting was at work on the Salisbury Plain. Stonehenge, far more than a simple solar calendar, captures the slow, more subtle rhythm of the moon. Its station stones and the larger architecture are aligned to the lunar standstill, an event that occurs only every 18.6 years when the moon reaches its most extreme rising and setting points on the horizon. This long cycle was deeply significant to its builders, likely marking a sacred rhythm of time that governed cultural and spiritual renewal. To track such a slow pulse required an engineering project that would endure for centuries, a permanent stone clock set to ring its bell for generations far into the future. Perhaps the most profound example of this long-range thinking comes from a much older site, the Nabta Playa stone circles in the Sahara. Over 7,000 years ago, before the pyramids were even a concept, a nomadic people arranged standing stones to track the precession of the equinoxes. This is the grandest celestial cycle of all, a 26,000-year wobble in Earth's axis that slowly shifts the entire sky. They were not just marking seasons. They were mapping the very ages of the world, using a circle of stones in the desert to measure a temporal wave so vast it would wash over countless human lifetimes. The sheer ambition is breathtaking. These engineers were building calendars meant to outlast languages, empires, and even climate shifts, for the Sahara was once a green savanna. They embedded alignments that would only become perfect millennia after their construction, creating a countdown to an age they would never see. this was not superstition. It was a sophisticated form of science, an attempt to model cosmic time itself in stone and shadow. They understood that the universe operates on predictable, mathematical rhythms, and that by locking those rhythms into the most permanent medium possible, they could send a message forward. That message was a warning and a reassurance that all things, even civilizations, move in cycles. This cyclical worldview was not confined to remote observatories, but was physically stamped onto the very layout of their greatest cities. The very streets of their cities were designed to speak. At Mohenjo-Daro and Harappa, the famous grid patterns were more than just efficient layouts. They contained mathematical ratios that defined the ideal spacing between homes, the width of streets, and the capacity of public wells. These were not arbitrary measurements. They were calculated models of a sustainable population density. As a city grew and new dwellings squeezed into the allotted spaces, the ratios would be disrupted. The engineered harmony of the grid would begin to show strain, with water access becoming unequal and movement through the streets becoming congested in predictable ways. The city itself became a living gauge, its layout a silent prophecy that when the mathematical balance was lost, the social fabric would soon follow. This principle of urban prophecy reached a grand scale at Teotihuacan. The city's central artery, the Avenue of the Dead, is aligned not just with a mountain sacred to rain, but also with the Pleiades star cluster. Its major structures, the pyramids of the sun and moon and the temple of the feathered serpent, are positioned according to a precise unit of measurement and complex geometric relationships. This layout encoded a profound understanding of systems. The distance from the center of power to the outermost residential compounds, the capacity of the irrigation channels that fed the city's farms, all of it was part of a calculated model. The engineers were mapping the relationship between centralized authority, the fair distribution of resources, and long-term stability. If the balance tipped too far, if the flow of goods was interrupted or hoarded, the city's very design predicted the social fractures that would inevitably appear. Even Roman practicality was infused with this forward-looking vision. Their famed sewer system, the Cloaca Maxima, and their extensive network of roads were engineered with built-in failure points. The gradient of an aqueduct, the thickness of a road's foundation, the diameter of a sewer pipe, all were calculated for a specific population and maintenance regime. The engineers knew that neglect was a form of future collapse. When a sewer channel, designed to be cleared at regular intervals, began to silt up beyond a certain point, it would cause backups in a predictable sequence, first affecting the lowest-lying neighborhoods. This was not an accident. It was a diagnostic tool engineered into the urban fabric, a clear signal that public health was being compromised by a failure of upkeep. The ziggurats of Mesopotamia tell a similar story of embedded time. These massive stepped pyramids were constructed with layers of mud brick and baked clay, materials chosen not just for availability but for the way they weather. The specific composition of the bricks and the patterns of their laying meant that erosion would occur in distinct stages. A skilled observer could look at the wear on a ziggurat's facade and read the history of environmental stress, the duration of dry periods, or the intensity of rare rainstorms that had scoured its sides over centuries. The structure itself became a stone ledger of climatic history, a permanent record of the challenges the city had endured. In every case, these ancient urban designers saw the city as a complex organism. They understood that its health was not a matter of chance, but a function of balance, maintenance, and respect for natural limits. They translated this understanding into stone, brick, and road, creating three-dimensional blueprints that modeled both success and failure. Their work was a remarkable fusion of immediate necessity and prophetic foresight, building warnings about societal vulnerability directly into the landscape of daily life. This profound temporal awareness even extended to the very materials they chose to build with. The very stones they chose were messengers. Ancient engineers understood that material science was not just about building for the present, but about crafting a dialogue with the future. They selected and processed their construction materials with an almost prophetic foresight, using the physical properties of stone and metal to encode powerful statements about durability and the passage of time. The Roman concrete used in their harbors is a perfect example. Modern researchers were baffled to discover that structures submerged in seawater for 2,000 years are not only intact but have actually grown stronger. The secret was a specific mixture of volcanic ash and lime that creates a rare mineral when it reacts with salt water. This was no accident. It was a deliberate recipe for eternity, a technological triumph that demonstrated a profound understanding of long-term material behavior, knowledge we are only now beginning to reclaim. This philosophy of permanence echoes in the baffling precision of Puma Punku in Bolivia. There, builders worked with a volcanic rock called andesite, cutting blocks with such exacting geometric perfection that the edges remain razor-sharp after thousands of years. The joints between stones are so tight that not even a blade can be inserted. This was more than a display of skill. It was a statement crafted in stone, a declaration that their work was meant to withstand not just the wear of seasons, but the violent shudder of earthquakes and the slow, grinding pressure of geological ages. The material itself was chosen for its resilience, and the cutting technique ensured that resilience would be communicated across millennia. In Egypt, the pyramid builders displayed a similar genius. They selected specific types of limestone and granite that weather in distinct, predictable patterns. As centuries pass, the stone surfaces erode in a way that creates a natural clock, a visual record of environmental exposure that can be read by those who know how to look. This was a built-in chronometer, tracking the passage of ages through the very skin of the monument. Further west, in the cities of the Maya, engineers developed sophisticated stucco compositions for their temples. These plasters were designed to be durable, yet they contained a hidden diagnostic feature. When subjected to prolonged drought, the mixture would contract and crack in a specific, recognizable pattern. The facade of a building could thus serve as a physical barometer, its surface telling a clear story of climate stress long after the civilization itself had passed. Even their metalwork carried a message for the future. The Moch metallurgists of ancient Peru created gold alloys of astonishing purity and complexity. These metals were not meant to remain untarnished. Instead, the specific composition of the alloys caused them to develop a patina, a slow-changing surface film that correlates directly with subtle shifts in atmospheric chemistry over centuries. A Moch artifact does not just gleam with lost wealth, it holds within its very surface a layered history of the air itself, a material witness to environmental changes across vast stretches of time. Every one of these choices was a profound philosophical act. By mastering materials that interacted with time in predictable ways, these ancient engineers were making a statement about what endures and what fades. They were building legacies meant to weather multiple civilizational cycles, creating objects and structures that would stand as stable reference points in a changing world. Their material science was a form of temporal messaging, and their command over physical substance was so complete that it even extended to the manipulation of sound itself. The stones themselves could sing. Ancient engineers mastered the physics of sound to create structures that whispered their warnings not in words, but in frequencies and echoes. At Chichen Itza, climbing the steps of the Great Pyramid produces a chirping echo that perfectly mimics the call of the sacred Quetzal bird. But this auditory miracle is not merely a clever trick. The sound is clearest and most resonant only when specific atmospheric conditions of temperature and humidity are present. In a time of environmental stress, as the local climate shifted and dried, the Quetzal's call from the stones would weaken or disappear entirely. The pyramid was an acoustic barometer, its voice a direct report on the health of the world around it. This was prophecy written not on a page but in the very air. Deep within the hypogeum of Malta, a labyrinthine underground sanctuary carved from solid rock, certain chambers resonate at specific low frequencies. These vibrations fall within a range that can physically affect human brainwave patterns, potentially altering states of consciousness. The builders calibrated this sonic environment with incredible precision. But they also understood that as the massive stone structure settled over millennia, as tiny cracks formed and the earth shifted, these resonant frequencies would change in a predictable way. The temple was not a static instrument. It was a living system, its shifting voice telling a story of geological time and structural age, a story only those who understood its original song could decipher. Even the magnificent Greek amphitheaters, celebrated for their crystal-clear acoustics, may have held a deeper prophetic function. Their perfect sound distribution was a mathematical model of social harmony. The design ensured that every citizen, regardless of their seat, could hear the proceedings clearly. Researchers suggest this engineering encoded a fundamental relationship between population size, effective communication, and civic stability. If the population grew too large for the theater's capacity, if people were forced to sit beyond the designed acoustic zone, the community would literally fall out of sync. The shared experience would fracture. The structure itself modeled the point at which a society becomes too large to maintain a single, coherent conversation. Across Europe, the passage tomb of Newgrange offers another sonic mystery. Its massive, corbelled stone chamber is engineered to resonate at specific frequencies when sunlight pierces its inner sanctum during the winter solstice. This was not random resonance. The builders created an audible marker for the celestial event, a humming stone chord that announced the sun's rebirth. The sound was as integral to the ceremony as the light itself, a permanent, repeatable sonic signature for one of the most important moments in their cosmic calendar. The most profound acoustic prophecies, however, may be found in temples with precisely positioned sound channels. These narrow stone conduits were designed to transmit only very specific frequencies, and they would only do so under exact conditions. Some were aligned so that they would act as sonic amplifiers only when a particular planet rose above the horizon or when the sun struck a certain angle. The temple would literally come alive with a specific tone only at a predicted celestial moment, turning architecture into an alarm clock set for a date thousands of years in the future. These ancient acoustic engineers understood that sound is a force deeply intertwined with the material world. They knew that the speed of sound changes with air temperature and density, and they built structures whose voices would change as the world changed. A long-term drought, a shift in seasonal patterns, even the slow settling of their own megalithic creations would alter the sonic message. They were not just building for their own ceremonies. They were creating environmental monitors and cosmic clocks that used the universal language of vibration to speak across the ages. This sophisticated manipulation of sound reveals a layer of prophetic engineering that is both subtle and profoundly powerful. And just as they encoded time in sound, they also etched the secrets of the cosmos into pure, timeless form. Their buildings were mathematical equations set in stone. Ancient engineers encoded their deepest understanding of the cosmos using a universal language that never fades or gets lost in translation, the language of sacred geometry. They understood that while words change and empires fall, the ratio of a circle's circumference to its diameter remains constant for all time. This is why we find the same precise mathematical relationships appearing in temples and monuments across the globe, from the proportions of the Parthenon in Greece to the intricate patterns of the Great Mosque of Kairouan. These builders were not merely pursuing aesthetic beauty. They were embedding eternal mathematical truths like the golden ratio and the Fibonacci sequence into their work as a permanent record. These constants are a bridge across millennia, a code that any advanced culture, no matter its spoken language, could eventually recognize and decipher. The geometric perfection was their method for sending a message forward, ensuring that the core of their knowledge would survive the collapse of their own age. This mathematical encoding reached its most elaborate expression in the mandala patterns of Hindu and Buddhist temples. These intricate designs are far more than decorative art. They are detailed maps of the cosmos, illustrating the structure of the universe and the cyclical nature of time itself. Every line, circle, and square within a mandala corresponds to a spiritual or cosmic principle, representing the endless cycles of creation, preservation, and dissolution. By walking the path of a mandala, a person moves through a symbolic representation of cosmic time. The engineers who designed these temples translated this profound cyclical worldview into physical form, creating a structure where architecture and cosmology become one. The very act of building was a way to make the invisible rhythms of the universe permanently visible. A similar genius animates the breathtaking tessellations of Islamic architecture. Those endlessly repeating geometric patterns, which cover walls and domes in a hypnotic dance of stars and polygons, are not random. They are visual representations of infinity and divine order, based on complex mathematical principles that model both the static perfection of the cosmos and the dynamic progression of time. The patterns are calculations made manifest. The fact that these same underlying geometric principles appear in sacred structures from Cambodia to Cordoba suggests a shared, perhaps instinctual, understanding that certain mathematical laws are the fundamental building blocks of reality itself. The architects were using their medium to communicate these discovered truths. Perhaps no structure demonstrates this principle more vividly than the Borobudur Temple in Indonesia. This massive pyramid is a three-dimensional mandala, its 9 stacked terraces leading pilgrims on a spiraling path toward enlightenment, but it is also a sophisticated stone calendar. The precise alignment of its stupas and statues creates specific optical effects and shadows that shift with the sun's journey across the sky throughout the year. On the equinoxes, for example, the interplay of light and stone reveals hidden alignments, turning the entire monument into a giant solar marker. The geometry of the structure captures the solar cycle, making the passage of time a tangible, visible experience for anyone walking its path. This was the ultimate goal of sacred geometry, to build eternity into temporal structures, to make stone speak the language of the stars. The mathematical sophistication on display is not just a relic of the past. It is a challenge to the future, a permanent invitation to understand the timeless patterns that govern our world. And just as they used perfect geometry to model cosmic order, these same engineers also embedded warnings within the deliberate flaws of their most brilliant designs. Even their greatest structures were designed to fail intelligently. Throughout the ancient world, master engineers built what appear to be flaws into their creations, not as oversights but as deliberate diagnostic features. The aqueducts channeling water into the rock-cut city of Petra contained sections made from a slightly more soluble limestone. These were not weak points born of poor planning. They were strategically placed sensors. If the surrounding environment began to degrade, perhaps from deforestation or changes in land use, the water flowing from the highlands would become more acidic. This increased acidity would selectively dissolve these specific limestone sections first, causing a collapse that would block the flow. The failure was a clear, unmistakable signal that the health of the watershed itself was in jeopardy long before the city's reservoirs ran dry. This philosophy of intentional vulnerability extended to the very foundations of Mesoamerican pyramids. At sites like Teotihuacan, engineers designed layered foundation systems using materials of differing compressibility. They were not building for a single lifetime, but for centuries. As seasons turned into generations, these foundations would settle, but not randomly. The specific pattern of this settlement, visible in the tilt of the massive stone structures above, would act as a permanent record. A uniform sinkage might be normal, but a distinct differential tilt would indicate serious underlying issues, such as soil erosion from mismanaged agriculture or the slow, silent shifting of seismic faults. The pyramid itself became a giant, stone-built inclinometer, its posture telling a story of geological stability or vulnerability. Roman road engineers applied this same foresight to their vast network of trade routes. They would occasionally incorporate short, diagnostic sections paved with a softer stone or a less durable concrete mix amidst the standard, rugged pavement. These sections were not mistakes. They were wear indicators. Under normal traffic, these patches would degrade at a predictable rate. But if trade intensified beyond sustainable levels, perhaps due to population pressure or military campaigns, the wear on these diagnostic sections would become dramatically accelerated. A road inspector centuries later could look at the differential erosion and read a clear history of economic strain, understanding that the empire had, at some point, pushed its logistical networks to a breaking point. In the humid climate of ancient Cambodia, the builders of Angkor designed temple drainage systems with an elegant prophetic feature. The complex networks of channels and spouts were engineered to handle typical monsoon rains. However, they also included hidden overflow passages, carved at a precise height within the walls. These channels would only see water if rainfall exceeded sustainable levels for an extended period, indicating a significant shift in climate patterns. The activation of these overflow routes would leave permanent watermarks and erosion patterns on the temple stone, a lasting testament left by the engineers that read, "When you see this, the rains have changed for the worse." Perhaps one of the most subtle examples comes from the placement of Egyptian obelisks. Certain obelisks were oriented so that the shadow they cast at the summer solstice would fall upon a specific marker on a nearby temple wall. This alignment was calibrated for a specific atmospheric clarity. During periods of prolonged drought, the air becomes filled with fine, suspended dust. This dust scatters the sunlight, subtly altering the sharpness and the precise endpoint of the obelisk's shadow. When the shadow no longer reached its intended mark with perfect clarity, it was a silent, public announcement that the land was entering a period of extreme aridity. The monument itself became a giant, functioning sundial and climate indicator. These were not prophecies of doom, but calibrated warnings. The ancient engineers understood that systems fail in predictable ways, and they had the courage to build those failure modes directly into their most magnificent achievements. They created structures that could diagnose their own decline, turning stone and mortar into active participants in long-term survival. This sophisticated form of risk assessment reveals a mindset that looked centuries ahead, embedding physical algorithms into the landscape to guide future generations. Their deep understanding of cause and effect even extended to the invisible flow of energy that powered their world. Their buildings were designed to feel the coming cold. Ancient engineers created structures that managed thermal and human energy with such precision that they became prophetic models of resource consumption. The ancestral Pueblones who built their dwellings into southwestern cliffs mastered a form of passive solar design that is still studied today. Their homes were oriented to capture the low winter sun for warmth, while the massive rock overhangs shaded them from the intense summer heat. This was more than comfort, it was a calibrated system. The thermal mass of the stone walls absorbed heat during the day and released it slowly at night, creating a stable microclimate. But this perfect balance was engineered for a specific climate profile. If average temperatures were to rise over centuries, or if seasonal patterns shifted, the solar angles would change. The carefully calculated overhangs would no longer provide adequate shade, and the dwellings would begin to overheat in predictable ways. The architecture itself contained a silent forecast, a built-in response that would only activate when the world outside had changed beyond its original parameters. This same foresight was engineered into the heart of Roman society, within the vast bath complexes that were central to daily life. The hypocaust systems that channeled hot air under floors and through walls were marvels of efficiency, but they were also voracious consumers of wood. The engineers designed these systems to operate at peak performance with a specific quality and quantity of fuel. As demand for this fuel grew with the empire and local forests were depleted, the system would begin to fail in a diagnostic sequence. The temperature gradients within the baths would become uneven, certain rooms would fail to heat properly, and the rate of fuel consumption needed to maintain comfort would skyrocket. This was not a random breakdown. It was a physical manifestation of an energy crisis, a clear signal that the civilization was consuming its foundational resources faster than they could be renewed. In the arid cities of ancient Persia, engineers solved the problem of heat with elegant wind-catching towers, or badgers. These structures funneled cool breezes down into buildings and courtyards, creating a natural and cost-free form of air conditioning. Their effectiveness, however, was entirely dependent on unimpeded airflow. The architects understood that urban growth posed the greatest threat to this free energy source. As a city expanded, new buildings would inevitably rise and alter the wind patterns. The badgers were engineered to be exquisitely sensitive to this change. A new structure built too close or a street that became more crowded would disrupt the airflow in a measurable way. The efficiency of the cooling would drop in a predictable correlation with increasing urban density. The towers stood as silent sentinels, their diminishing performance charting the city's march toward unsustainable congestion. These were not isolated inventions. They represent a unified understanding that energy management is the bedrock of civilization. The sophisticated water clocks of ancient China made this relationship explicit. These intricate machines used the steady flow of water to power gears and tell time with remarkable accuracy. The engineers, however, built in mechanisms that would falter in specific ways if the water supply became inconsistent or slowed. A gear would slip, a display would freeze, all indicating that the hydraulic source could no longer support the technological complexity it powered. The machine's failure was a direct analogy for societal strain. This integration of energy management with prophetic engineering reveals a holistic worldview. These master builders saw their cities as living organisms dependent on a constant flow of resources. They designed their systems not just for immediate function, but as long-term gauges, embedding performance thresholds that would signal when a society was approaching its ecological and logistical limits. Their work demonstrates that the most profound warnings are not always carved in stone, but are often written in the silent language of failing warmth, stilled air, and faltering machines. This deep understanding of systemic vulnerability extended even further, shaping the very walls built to protect a civilization from external threats. Their walls were designed to be read like a history book written in stone. The defensive engineers of antiquity constructed fortifications that served a dual purpose, providing immediate security while also embedding long-term prophecies about the evolution of conflict itself. The famous concentric walls of Constantinople were more than just layered barriers. Each new ring represented a different era of siege technology, from simple battering rams to complex trebuchets. The spacing between these walls, the angles of the bastions, and the thickness of the stone were all calculated responses to specific threats, but the design also looked forward. It modeled a future where attackers would develop even more powerful weapons, forcing defenders to rely on deeper, more complex layers of defense. The architecture was a physical prediction that security is never static, but a constant race between protection and penetration. This principle of adaptive forecasting was engineered into the very fabric of European castles. Some designs included what appeared to be weak points, a section of wall built with slightly inferior mortar or a gatehouse with a vulnerable angle. These were not flaws, they were diagnostic features, controlled failure mechanisms. Invading armies would naturally focus their assault on these apparent weaknesses. The castle's design funneled the attack to these predetermined spots, which were engineered to fail in a specific, containable way. This controlled failure gave the defenders critical information. It revealed the latest siege tactics and the power of new weapons, all while protecting the castle's core. It was a way for the structure to test itself against the changing face of war and report the results to future generations of military architects. Across the world, the builders of Great Zimbabwe demonstrated a similar foresight. Their massive, dry stone enclosures were constructed without mortar, using a meticulous method of stone shaping and stacking. The stability of these walls was entirely dependent on skilled, consistent maintenance. The engineers designed them so that periods of social neglect or internal conflict would leave a clear, physical signature. When maintenance crews were diverted or social order broke down, the walls would begin to deteriorate in a distinct pattern. Certain types of stones would shift first, and specific joints would fail, creating a visible record of civil unrest etched directly into the architecture. The wall itself became a stone chronicle of the kingdom's political health. This predictive genius extended to the sophisticated gate systems of Hittite cities. Their fortifications featured complex entryways with multiple choke points, hidden sally ports, and overhead murder holes. The true brilliance was in the sequencing. These defensive elements were designed to engage in a specific order, creating a physical algorithm for urban defense. If the first gate fell too quickly, it signaled that the enemy had developed new methods for breaching primary defenses, triggering a pre-planned response for the inner layers. The failure of one component automatically activated the next phase of the defensive protocol. The gate system was a mechanical brain, processing the threat level and adjusting the city's response in real time. Its very operation a forecast of how a siege would logically unfold. Even the vast scale of the Great Wall of China encoded a grand prediction about connectivity and isolation. The placement of its watchtowers was not random. They were positioned at precise intervals calculated for optimal communication by signal fire or flag. This distance was a careful balance between speed of messaging and the resources needed to maintain the chain of communication. The system contained a built-in prophecy. If the empire could not consistently staff and supply these towers, the gaps in communication would grow. The failure of a single tower would create a blind spot, and the pattern of these failures would map the empire's weakening grip on its frontier. The wall was not just a barrier against invaders, it was a giant stone-built network model, its health directly reflecting the administrative and logistical strength of the civilization it protected. These defensive engineers viewed conflict as a recurring challenge with predictable patterns. They understood that the tools of war would evolve, but the fundamental dynamics of attack and defense, of social cohesion and breakdown, would follow recognizable cycles. Their structures were therefore built to be both shields and sensors, designed to withstand immediate assault while simultaneously gathering data on the long-term tides of history. This deep understanding of connectivity extended beyond walls and towers, shaping the very roads that bound ancient empires together. The long, straight lines of Roman roads were far more than pathways for legions. They were prophetic instruments engineered to take the pulse of an empire. Beneath their stone surfaces lay intricate layered foundations and sophisticated side ditches designed for perfect drainage, a system that would only function flawlessly with regular, organized maintenance. When this upkeep began to falter, the roads themselves told the story. Water would seep into the subbase, causing the stones to settle in a distinct, predictable pattern. The failure would start not in the busy heart of the empire, but along its distant frontiers, the routes most vulnerable to neglect. A crumbling road in a distant province was not just a local inconvenience, it was a diagnostic signal, a physical manifestation of waning political control and shrinking economic reach. The empire's connectivity was literally unraveling from the edges inward, and the engineers had built this prophecy directly into the landscape. High in the Andes, the Inca engineered a different kind of prophetic network. Their mountain trails and suspension bridges were marvels of adaptation, but they were also exquisitely calibrated to their social context. The bridges, woven from native grasses, required entire villages to participate in their annual renewal. This was not just a practical necessity, it was a built-in measure of community cohesion. If social bonds frayed or labor was diverted to constant conflict, the maintenance cycle would be broken. The bridges would then deteriorate not randomly but in a specific sequence. The central cables would weaken first, making the crossing unstable long before a complete collapse. This gradual failure gave a clear, visible warning. It signaled that the social fabric essential for maintaining this high-altitude world was itself under strain. The network's health was a direct reflection of the people's unity. This understanding of optimal connection shaped even the spacing of desert-way stations along the Silk Road. The caravanserais were positioned at distances calculated for a camel's endurance, but this distance also represented a precise economic equation. It was the maximum sustainable gap between oases of trade and security. If political turmoil or environmental shift made travel more dangerous, if the flow of goods slowed below a critical threshold, then that calculated distance became a deadly void. A caravanserai that was once a welcome refuge would fall into silence and disrepair, not because of a single catastrophe, but because the density of connectivity that justified its existence had evaporated. The empty spaces between these structures began to speak, telling a story of a network contracting, of worlds slowly drifting apart. Perhaps the most silent and powerful of these connectivity prophets were the ancient ports. The great harbor of Carthage was engineered with clever water channels designed to flush away silt and maintain a deep berth for trading vessels. This system functioned perfectly only with a constant stream of maritime traffic, the very movement of ships helping to circulate the water. When trade patterns shifted or declined, the circulation slowed. Silt would then accumulate in a distinct, measurable pattern, slowly choking the harbor. The harbor's death was not sudden. It was a gradual filling of the arteries, a direct physical consequence of a diminishing pulse of exchange. The layers of sediment laid down in these ports form a geological record of prosperity and isolation, a prophecy written in mud and stone by engineers who understood that civilizations are built not just on grand monuments, but on the constant, vital flow of connection. And just as they mapped the flow of goods and people, these same visionary engineers turned their attention to the most fundamental flow of all, the one that feeds every civilization, the flow of life from the soil itself. Their fields were designed to speak the language of the land. Ancient agricultural engineers transformed entire landscapes into prophetic systems, creating food production networks that doubled as long-term environmental monitors. The breathtaking rice terraces of Southeast Asia, carved into mountainsides over generations, were far more than just farms. Their intricate hydraulic systems of bamboo pipes and stone channels were calibrated with the precision of a scientific instrument. These channels were engineered to deliver a specific, optimal flow of water to each level of the terrace. If deforestation in the uplands accelerated soil erosion, the silt would begin to accumulate in these channels, altering the water flow in a predictable sequence. The highest terraces would be the first to show signs of water stress, their rice stalks wilting not from a lack of rain, but from a silent, creeping imbalance in the watershed. The system was a living gauge, its failing health a clear warning that the foundation of their agriculture was being undermined. This same prophetic foresight floated upon the lakes of the Aztec Empire. Their chinampas, or floating gardens, were artificial islands of incredible fertility. The engineers who created them understood that their productivity was tied directly to the quality of the lake water itself. They designed the chinampas to produce specific, predictable yield patterns season after season. As the surrounding city grew and water quality gradually deteriorated from urban waste, the gardens would respond in a diagnostic fashion. Certain crops would begin to fail first, those most sensitive to water purity. The yield would not drop randomly, but in a distinct sequence that mirrored the increasing contamination. The gardens were a biological testing station, their changing harvests spelling out a slow-motion message about the environmental cost of urban expansion. Perhaps one of the most elegant examples of this embedded wisdom comes from the qanat systems of ancient Persia. These underground tunnels, sometimes stretching for miles, tapped into mountain aquifers and delivered water to arid fields by gravity alone. The genius of their design included subtle vertical shafts that also served as monitoring stations. The engineers could measure the water table's height in these shafts with simple markers. A sustained drop in the water level below a certain point was a critical signal. It indicated that the community was extracting groundwater faster than the aquifer could recharge, a problem that would take generations to become a crisis. The qanat was not just a water source, it was a long-term ledger of resource balance, its very flow a prophecy about sustainable living. In ancient Sri Lanka, engineers created a cascading civilization sustained by vast, sophisticated irrigation works. Their intricate networks of tanks and canals featured brilliantly designed sluice gates, known as Bisakatuwa, which regulated water flow with remarkable precision. These gates, however, were also exquisitely sensitive to the health of the environment. They were engineered to operate flawlessly with water of a certain clarity. When upstream land management failed and soil erosion increased, the sediment load in the water would rise. At a critical threshold, this silt would begin to interfere with the precise operation of the sluice mechanisms, causing them to stick or fail in a specific, recognizable pattern. The failure was not a random breakdown, it was a coded message pointing directly to the root cause: severe watershed degradation. The system was designed to break in an informative way, forcing a conversation about the land that fed it. These agricultural visionaries saw their fields and waterways as parts of a single, breathing organism. They understood that food security was not just about the harvest of a single season, but about maintaining a delicate, long-term pact with the natural world. Their engineering was a form of dialogue with the future, embedding measurable indicators of ecological health directly into the landscape that sustained them. They built systems that would not only feed their people but would also teach their descendants, using the universal language of water, soil, and plant growth to warn of coming hardship. This profound connection to the cycles of life naturally extended into the spiritual realm, where they encoded similar prophecies not in soil, but in stone and ceremony. These sacred spaces were designed to evolve alongside human consciousness. In Egypt, the great temple of Karnak was not a static monument but a living, breathing chronicle of faith. Its central axis was aligned with the rising of the midwinter sun, but the slow drift of precession meant this alignment would gradually shift over centuries. The priests and engineers who oversaw its expansions knew this. They built in a way that the temple's relationship with the cosmos would change, marking the inevitable transition from one religious era to the next. The structure itself was a celestial clock counting down to a future age when the old gods might be understood in a new light, or perhaps even replaced. This was not a loss of faith, but a built-in prophecy of its natural transformation. We see this same principle of layered prophecy at Stonehenge. Its construction did not happen all at once, but in distinct phases spanning over 1,000 years. Each new arrangement of stones reflected a deeper, more complex understanding of the cosmos. The shift from the simpler earthworks to the massive sarsen trilithons was a physical prediction. It encoded the belief that future generations would develop a more sophisticated cosmology, one that required a more precise and grand instrument to measure the heavens. The monument anticipated its own intellectual obsolescence and planned for its future upgrade, stone by stone. This concept of spiritual evolution was made literally concrete in the pyramids of the Maya. At sites like Tikal, archaeologists find pyramids built in layers like nesting dolls. A new, larger temple would be constructed directly over an older, smaller one. This was more than just practical renovation. It was a physical doctrine, a stone-carved lesson that belief systems are not discarded but built upon. Each new layer represented a cultural prediction that the community's understanding of the divine would grow and transform, and that the sacred space must be capable of containing this future growth without erasing its own history. Even the artistic experience was subject to this prophetic engineering. The acoustics of the theater of Epidaurus in Greece are so perfect that a whisper on the stage can be heard in the back row. This was not just a triumph of sound design, it was a prediction about the future of storytelling. The engineers calibrated the space for the human voice, anticipating a time when large communities would need to share a collective emotional experience. The architecture itself fostered a shift from small, private rituals to large, public performances, predicting the evolution of religion into drama and civic ceremony. The space was prepared for a future where moral lessons would be conveyed not just by priests, but by actors and playwrights. Hidden beneath the streets of Roman cities, the temples of Mithras held a different kind of celestial secret. These underground sanctuaries were often aligned with the sun's position on the god's feast day. However, some contained additional, more subtle alignments pointing to stars that, due to precession, would only culminate directly over the altar centuries later. The initiates who built them were creating a timed revelation. They embedded a message for a future generation, a moment when the heavens would finally complete the temple's sacred geometry and trigger a new understanding of their mysteries. These ritual structures were, in essence, machines for managing cultural time. The ancient engineers who designed them displayed a profound insight that while stone endures, human belief is fluid. They did not try to freeze their own era in place. Instead, they built flexible sacred spaces that could hold multiple meanings across generations. They created architectures of anticipation, confident that future minds would arrive at their own revelations within the prophetic frames they had left behind. And just as they designed temples to preserve spiritual memory, they also developed ingenious systems to protect practical knowledge from the ravages of time. Their most precious resource was not gold, but memory itself. Ancient engineers understood that knowledge is the most fragile pillar of civilization, and they designed entire systems to protect it, systems that prophetically modeled how information would be lost and found again across the ages. The legendary Library of Alexandria was far more than a warehouse for scrolls. Its architects engineered the very air within its halls, creating subterranean channels that circulated cool water to maintain a constant temperature and humidity level, an ideal climate for preserving fragile papyrus. But they also built in silent sentinels. Certain structural elements were designed to show the first signs of moisture damage or pest infestation long before the precious texts were affected. A specific type of wood used in a shelf support might warp in a distinct pattern when the humidity rose beyond the safe threshold. The building itself was a guardian, its own subtle deterioration sounding an early alarm that the knowledge within was entering a period of grave danger. This understanding of systemic vulnerability shaped knowledge preservation across the ancient world. In Mesopotamia, the great clay tablet libraries were not concentrated in a single, vulnerable capital. Scribes created duplicate collections of essential texts on astronomy, law, and medicine, distributing them to cities across the empire. This was a deliberate redundancy protocol, an anticipation that political collapse or conflict could erase a single central repository. They were engineering informational resilience, ensuring that even if one city fell into silence, the core of their learning would survive elsewhere, waiting to be rediscovered. The system predicted the fragility of centralized knowledge and built a solution directly into their administrative practices. This same foresight was woven into the very fabric of oral traditions. Cultures without writing developed incredibly sophisticated mnemonic systems, turning vital information into rhythmic poetry, song, and story that could be passed down with remarkable accuracy. But the true engineering genius often lay in the triggers they built into the landscape. A specific rock formation, a peculiar bend in a river, or the alignment of a standing stone might serve as a memory cue for a lengthy epic or a complex genealogical record. The knowledge was not just in the minds of the people, but in the dialogue between their stories and the permanent features of their world. This created a distributed backup system where the land itself helped to preserve cultural memory, ensuring that even if the people were scattered, returning to these places could reactivate the stories. One of the most ambitious attempts to speak to the future comes from the silent, subterranean army of China's first emperor. The terracotta army is often seen as a display of power, but it was also a profound knowledge preservation project. Each soldier's unique face, their detailed armor, their precise formations, and the weapons they held constituted a vast library of cultural and military information cast in baked clay. The engineers who designed this army were creating a three-dimensional record that could be read by anyone, regardless of their language or era. It was a physical archive of a civilization's technology, social structure, and artistic achievement, buried not for the dead, but for the future, a message in a bottle made of thousands of silent, earthware witnesses. The common thread in all these systems is a prophetic understanding of information decay. These ancient librarians and engineers did not believe knowledge was safe. They knew it was perpetually under threat from fire, water, war, and simple neglect, so they designed their preservation methods with built-in failure indicators and multiple layers of redundancy. They created systems that would degrade in predictable, diagnosable ways, giving future generations clear signals about what was being lost and perhaps how to save it. This was not just archiving, it was a form of temporal engineering, a deep understanding that the flow of information across centuries is a force that can be measured, modeled, and guided. Their sophisticated approach to managing knowledge across civilizational cycles continues to inform our own digital preservation strategies today. And just as they safeguarded knowledge on land, these visionary engineers also encoded their predictions into the very ships that ventured beyond the horizon. Their ships were engineered to read the ocean's mood. Ancient maritime engineers crafted vessels that were not merely transportation, but complex instruments encoding predictions about the future of exploration itself. The great Polynesian voyaging canoes, which navigated vast stretches of the Pacific using the stars, winds, and swells, were masterpieces of sustainable design. Their hulls were lashed together with complex, flexible cordage, a technique that allowed the ship to ride massive ocean swells without breaking apart. This lashing, however, was the system's prophetic heart. The specific types of natural fibers used would deteriorate in a precise sequence if the traditional knowledge of harvesting and treating them was lost. If a new generation began using inferior materials or incorrect weaving patterns, the lashings would loosen prematurely during a voyage. The failure was a clear, physical signal that the sacred chain of navigational wisdom was being broken, threatening the entire enterprise of long-distance exploration. The vessel itself became a teacher, its structure testing the crew's fidelity to ancestral knowledge with every league they traveled. On the other side of the world, Roman merchant ships carried a different kind of warning in their very frames. Their hulls were built with a calculated balance of strength and flexibility, using specific woods and joinery techniques designed for the predictable rhythms of Mediterranean trade routes. These ships were engineered to withstand a certain number of loading and unloading cycles, a specific intensity of storms, and a precise schedule of maintenance in dry dock. When the empire's economy began to strain, pushing these vessels beyond their designed limits, they would fail in diagnostic ways. Keels would splinter along predictable grain lines, and planks would spring leaks at specific stress points. This was not random wear and tear. It was a built-in prophecy, a physical manifestation of an overextended trade network, where the relentless demand for goods was literally breaking the backs of the ships that carried them. These maritime prophets understood that the sea offered both connection and profound isolation. This duality was engineered into the very coastlines they inhabited. The legendary lighthouse of Alexandria, towering over the ancient harbor, was far more than a simple fire on a platform. Its architects designed the mirror and lens system to project a beam of a specific intensity and range. This brilliance was calibrated for the typical atmospheric clarity of the region. When prolonged drought filled the air with fine dust, or when unusual humidity created a thick haze, the beacon's visible range would diminish in a measurable way. The lighthouse was an environmental sentinel, its dimming light a silent warning to all approaching ships that the familiar, safe conditions for navigation were changing, that the very air and sea were speaking a new and more dangerous language. The dockyards of ancient Carthage held similar prophecies in their stone. Their cleverly designed harbor facilities included channels and sluice gates intended to flush away silt and maintain a deep, clear berth for the city's mighty fleet. This system, however, functioned optimally only with a constant, vigorous flow of maritime traffic. The movement of ships in and out of the harbor itself helped to circulate the water and prevent sedimentation. When trade routes shifted or political power waned, reducing the number of vessels, the circulation would slow. Silt would then accumulate in a distinct, layered pattern, slowly choking the harbor's vitality. The death of the port was not a sudden catastrophe, but a gradual suffocation recorded in the mud, a direct physical consequence of a diminishing pulse of cultural exchange. The engineers had built a model of connectivity into the landscape, and its failure wrote a clear history of isolation. From the lashed hulls of the Pacific to the silted harbors of the Mediterranean, these maritime creations testify to a profound foresight. The ancient shipwrights and harbor masters saw the ocean not as a void, but as a dynamic stage for human ambition. They knew that the drive to explore was eternal, but that its success depended on a delicate balance of knowledge, resources, and environmental stability. They encoded this understanding into their most advanced technologies, creating vessels and ports that would not only carry them across the waves, but would also carry a message forward about the enduring vulnerabilities and triumphs of a connected world. This same visionary approach to materials and their limits defined their work with metal, where they forged prophecies in fire and ore. Their mastery of fire and ore created prophecies in metal. Ancient metallurgists were not just crafting tools and treasures, they were encoding the entire life cycle of their technology into the very structure of their creations. Consider the legendary blades of Damascus steel, famous for their watery, swirling patterns and impossible sharpness. Achieving this was not a simple recipe. It required a specific type of iron ore rich in rare trace elements, a precise and repeated process of folding and forging at exact temperatures, and a final quenching that had to be timed to the second. The beautiful patterns themselves were a built-in quality control. If any step in this complex chain was compromised, if the ore quality dropped or the smith's knowledge was incomplete, the distinctive waves would fail to appear. The finished blade was therefore a perfect indicator of a civilization's peak technological capability. It silently declared that mining, chemistry, thermodynamics, and artisan skill had all converged at a high level. The metal itself was a witness to a golden age of craft. This same diagnostic principle was at work in the magnificent bronze vessels of ancient China. Their creation involved complex alloys of copper, tin, and lead, mixed in precise ratios that were recorded in court documents. The metallurgists who formulated these recipes understood that the supply of these metals was vulnerable. Tin, especially, often came from distant mines through long and fragile trade routes. They designed their bronze compositions so that if trade was disrupted and tin became scarce, later generations would be forced to use different, inferior ratios. These altered alloys would then corrode in a distinct, recognizable pattern, very different from the stable patina of a properly made vessel. A corroded cauldron was not just an old object, it was a mineral record of economic collapse, its green crust spelling out a story of broken connections and resource scarcity for anyone who knew how to read its surface. Perhaps the most silent and enduring of these metallic witnesses is the Iron Pillar of Delhi. Standing for over 16 centuries without rusting, it is a monument to a profound understanding of material science. Modern analysis shows its composition includes a protective layer that forms naturally, a result of its specific phosphorus content and the skill of its forgers. This was not an accident. It was a deliberate engineering achievement, a benchmark set in iron. The pillar's flawless condition serves as a permanent measure of technological maintenance. If the environmental conditions around it were to change drastically due to industrialization or pollution, if the knowledge needed to preserve it were ever lost, the pillar would eventually begin to show its age. Its continued resilience is a quiet, ongoing conversation between the ancient engineers and the present, a testament to their success in creating something meant to outlast the rise and fall of empires. Even the smallest metal objects carried this prophetic weight. The coins of ancient Greece were struck with detailed images of gods and heroes, but their true message was in their substance. The law demanded coins of a specific weight and purity of silver. During times of war or crisis, however, city-states would sometimes debase their currency, mixing in cheaper metals like copper to stretch their treasuries. This deception was recorded in the coins themselves. As they circulated, the copper would rise to the surface, creating a reddish tint, or the softer, impure metal would wear down more quickly, blurring the intricate stamps. A pile of coins from a certain era can be read like a history book. The gradual degradation of their quality maps the timeline of a city's desperation, its financial stability literally wearing thin. The metallurgists and minters who set the original standard had, in effect, created a system that would visibly fail, providing a clear economic diagnosis for future generations. These metalworkers understood that technology is never isolated. It exists in a delicate balance with natural resources, economic systems, and cultural priorities. A perfect sword required a stable mining industry. A pristine bronze vessel depended on secure trade routes. A rust-free iron pillar testified to lasting environmental knowledge. They engineered their artifacts to be more than objects. They made them into durable gauges, designed to measure the health of the complex civilization that produced them. Their legacy in metal challenges us to consider what our own creations will say about us millennia from now. And just as they encoded prophecies in forged metal, these same cultures wove their foresight into the very fabric of their society through the intricate art of textile production. Their fabrics were woven with economic foresight. Ancient textile engineers transformed the simple act of making cloth into a sophisticated language of prophecy, encoding predictions about trade, resources, and social stability directly into their threads and dyes. In the Andes, weavers created intricate textiles using patterns that were far more than decorative. These complex geometric designs functioned as mathematical codes, documenting the precise steps for optimal weaving, the exact ratios of dye materials to water, and the maximum sustainable rate of wool production from their alpaca herds. If a community began to overharvest dyestuffs or push their herds beyond capacity, the resulting fabrics would tell the story. The colors might become inconsistent, or the pattern's mathematical perfection would falter, serving as a tangible, wearable record that the economic balance had been lost. The cloth itself was a ledger, its beauty contingent on sustainable practice. This principle of embedded diagnostics reached an industrial scale in the silk workshops of ancient China. The entire system, from mulberry tree cultivation to the delicate rearing of silkworms, was a calibrated engine of production. The engineers who designed these processes understood that every element had a breaking point. Mulberry trees required specific soil conditions and a careful harvesting rotation to avoid exhaustion. If demand for silk grew too rapidly, leading to overcultivation, the leaves would lose their nutritional quality. The silkworms, in turn, would produce weaker, thinner threads that were more prone to breaking on the loom. This failure was not random. It followed a predictable sequence, a clear signal that the economic engine was being pushed beyond its natural limits. The quality of the silk itself became a real-time report on the health of the entire production chain. Across the Mediterranean, the legendary purple dyers of Phoenicia engineered their famous hues with similar foresight. Achieving those vibrant, color-fast shades required specific mordants, chemical compounds that bind dye to fabric. These mordants were often derived from rare minerals or processed urine, sourced through long and complex trade networks. The master dyers developed recipes that would only remain stable if these specific ingredients were used. If trade routes were disrupted, forcing the use of inferior substitutes, the legendary purple would begin to fade or change color in a distinct, recognizable pattern. A faded tunic was more than a worn garment. It was a map of broken economic connections, its altered hue a silent testament to a world grown smaller and more isolated. Even the looms themselves were prophetic machines. The sophisticated drawlooms used to create complex patterns contained delicate mechanisms that required regular, skilled maintenance to function correctly. The engineers who built them designed these machines to fail intelligently under economic stress. If a society could no longer support the apprenticeship system needed to train master weavers, or if economic pressures forced a shift toward faster, cheaper production, the looms would respond. Specific heddles would break first, certain tensions would fail, and the intricate patterns would begin to distort in a diagnostic sequence. The machinery's deterioration physically manifested the decline of specialized knowledge and the corner cutting of a strained economy. Through every spun thread and dyed pattern, these ancient textile artists demonstrated a profound understanding. They saw that the production of fabric was a microcosm of the entire civilization, a complex dance of resource management, labor organization, and long-distance trade. They engineered their processes not just for the present, but as living systems that would document the rise and fall of economic order. The enduring legacy of their work invites us to see the artifacts of daily life not as simple objects, but as woven narratives about the societies that created them. This same prophetic intention was pressed into the very clay that held their food and drink. Their pots were designed to preserve the voice of a people. Across the ancient world, ceramic engineers transformed humble clay into sophisticated cultural barometers, creating vessels that silently recorded the health of the societies that made them. The master potters of ancient Greece perfected the black figure and red figure techniques, processes that relied on a precise choreography of clay composition, oxygen levels in the kiln, and the application of specific slips. This was not just an artistic choice, it was a calibrated system. The resulting surface sheen and distinctive colors were a signature of peak technological and artistic knowledge. If the trade routes supplying the special clays were disrupted, or if the complex firing knowledge failed to pass completely to the next generation, the pottery would bear the marks of this loss. The famous black glaze would become dull or flake off in a distinct pattern, and the red backgrounds would turn muddy. Each flawed pot was a diagnostic artifact, its surface telling a clear story of cultural continuity or a break in the chain of tradition. In the Indus Valley, a similar foresight was baked into every terracotta object. Their production required a precise mixture of local clays and tempering materials, fired at a specific temperature range achieved through generations of refined kiln design. The engineers who developed these methods built in a silent alarm. If social stability wavered and the careful gathering of these specific materials was interrupted, potters would be forced to use inferior substitutes. The resulting vessels would be more fragile, developing fine cracks during firing or breaking under normal use. A pile of shattered pottery at an archaeological site is not just garbage. It is a layered record of resource stress, a physical manifestation of a society that could no longer maintain the sophisticated, everyday practices that defined its civilization. This predictive engineering reached its zenith in the glazed ceramics of ancient Mesopotamia. Their vibrant glazes were complex chemical achievements, using specific ratios of metals like copper and cobalt to create stunning blues and greens. The master potters understood that these glazes were sensitive to their environment. They engineered them to interact with time and the elements in a communicative way. If the climate became more arid or if the chemical knowledge was diluted over generations, the glazes would respond predictably. They might craze, forming a distinctive spiderweb pattern, or their colors would fade and shift in a recognizable sequence. A crazed glaze is more than a sign of age. It is a message from the past, a coded report on environmental conditions and the state of technological knowledge centuries ago. Perhaps no culture better exemplifies this than ancient China, where the quest for perfect porcelain became a national obsession. The process was a high-wire act of material science, requiring incredibly pure kaolin clay, precise control over kiln temperatures soaring to unimaginable heights, and a mastery of glazes that seemed to capture light itself. This system was a pyramid of interdependent knowledge. The engineers designed it so that any decline in standards would produce clear, diagnostic failures. If the clay purification process was rushed, microscopic impurities would cause the finished piece to warp or even explode in the kiln. If the temperature control slipped by even a small margin, the iconic translucent quality would be lost, replaced by a dull, opaque finish. Each imperfect piece was a signal, a physical indicator that the cultural discipline required for such excellence was under strain. The porcelain itself became a measure of civilizational focus. These ceramic engineers viewed every pot, plate, and tile as a potential time capsule. They understood that while temples might fall and libraries burn, broken pieces of pottery survive in the soil for millennia. They chose this most common of artifacts to carry their most enduring messages about daily life. The clay was their parchment, the kiln their publishing house, and the resulting vessel was a book written in the language of chemistry, thermodynamics, and cultural priority. It was a brilliant strategy for speaking to the future, using the objects of everyday existence to document the rise and fall of technological grace. This same insightful approach to encoding social patterns can be found in a surprising place: the games and recreational spaces they designed for their communities. Even the games they played were engineered to forecast the future of their society. Across the ancient world, recreational spaces and the rules of play were carefully crafted to serve as diagnostic tools, measuring the pulse of social cohesion and cultural priorities. In Mesoamerica, the great ball courts were far more than sporting arenas. Their towering parallel walls were positioned to create a distinct acoustic phenomenon, a deep echo that would resonate perfectly only when the stone surfaces were clean and the surrounding plazas were filled with a unified, attentive community. This specific sound required a certain level of maintenance and a shared focus on the sacred ritual of the game. If social bonds frayed and the community's attention turned elsewhere, the necessary upkeep would be neglected. The walls would accumulate debris and the perfect echo would falter and die. The court itself was a sonic barometer, its voice weakening in direct proportion to the fragmentation of the society it served. This principle of engineered leisure extended to the colossal Roman amphitheaters. These structures were marvels of crowd management, with specific vomitoria for efficient entry and exit and tiered seating that reinforced the social hierarchy. The very materials used in their construction told a story. The arena floor, for instance, was built to withstand specific intensities of use, from gladiatorial combat to elaborate animal hunts. When public tastes began to shift away from these grand, state-sponsored spectacles, the pattern of wear and tear on the structure would change. Sections of seating reserved for the upper classes might show less maintenance, while the structural elements supporting the hypogeum, the underground network of tunnels and cages, would begin to decay in a distinct, predictable sequence. The building's physical decline mapped the empire's evolving relationship with public entertainment and its changing social organization. The ancient engineers who designed the original Olympic facilities in Greece embedded a similar prophecy in their running tracks and wrestling grounds. The facilities were constructed to host a pan-Hellenic gathering, requiring cooperation and a sacred truce among frequently warring city-states. The materials chosen for the starting line of the stadium, the specific stone of the wrestling palestra, and the water channels for the baths were all selected for their durability under a strict, shared maintenance schedule. This schedule was a physical manifestation of cultural agreement. If political tensions escalated and the cooperative spirit of the games waned, the maintenance of these shared spaces would be the first casualty. The decay would not be random. The starting line blocks would shift, the palestra's surface would become uneven, and the water channels would silt up. The deteriorating facility was a clear, physical signal that the bonds of shared culture were unraveling. This predictive engineering was not confined to grand arenas. It was present on the game boards of everyday life. The royal game of from Mesopotamia and the Egyptian game of Senet were not mere pastimes. Their boards were laid out with mathematically significant paths, and their rules encoded sophisticated models of strategy and chance. The movement of pieces across these boards represented a microcosm of social decision-making, modeling concepts of risk, reward, and the interplay between fate and skill. The very existence of these complex games, with their standardized rules spread across vast distances, indicated a shared cultural language. A decline in the quality of the game boards, or a simplification of their rules found in the archaeological record, could signal a broader societal shift away from strategic long-term thinking or a breakdown in the cultural networks that sustained such shared intellectual pursuits. These ancient recreation engineers possessed a profound insight that how a society chooses to play reveals everything about its underlying health. They built their courts, stadiums, and game boards as permanent monitors, designed to thrive only during periods of unity, shared purpose, and cultural vitality. Their silent structures waited, their perfect acoustics, their pristine surfaces, and their complex rules all serving as a calibrated measure of the human spirit. And just as they engineered spaces for the living to gauge the health of their society, they applied the same foresight to the resting places they prepared for the departed. The silence within a tomb speaks volumes about the world outside. Ancient funerary engineers transformed burial sites into sophisticated instruments, designed not just to honor the departed, but to measure the pulse of cultural memory across centuries. The Egyptian pyramids offer the most stunning example. Their narrow air shafts aligned with stars like Theban, a celestial body that held the position of pole star only for a specific window in the 26,000-year cycle of precession. This was not an alignment for the pharaoh's own time, but one calculated to become perfectly true millennia later. The pyramid was a stone timepiece, its architecture marking a future date when the connection between the earthly and eternal realms would be mathematically reaffirmed, a prophecy in granite and limestone about the enduring nature of the soul's journey. Across Neolithic Europe, a different kind of prophecy was being interred within earthen mounds. These barrows were not simple piles of soil. They were engineered with precise layers of chalk, clay, and gravel, creating a specific hydrological balance that would preserve their contents in a predictable manner. The builders understood that the rate of organic decay within the mound would act as a clock, documenting the passage of time and the changing attitudes of future generations. If a society continued to maintain the site and honor its purpose, the mound would remain intact, its internal environment stable. But if cultural memory faded and the mound was neglected, the engineered drainage would fail in a distinct sequence. Water would seep through in a new pattern, accelerating decay in a way that left a clear archaeological signature. The mound itself recorded the duration and intensity of remembrance, its soil composition becoming a permanent ledger of respect or forgetfulness. This philosophy of engineered legacy extended deep beneath the streets of ancient Rome. The vast networks of catacombs were marvels of subterranean construction, with ventilation shafts and structural arches designed to maintain a specific atmosphere of reverence and permanence. The engineers who designed them built in subtle failure points. The ventilation systems, for instance, were calibrated to function only with regular maintenance and a steady flow of respectful visitors. If burial customs changed dramatically, or if periods of hardship led to the catacombs being sealed and forgotten, the air quality would deteriorate in a measurable way. Molds would grow in specific patterns on the walls, and certain types of stone supports would erode first, creating a physical record of the site's abandonment. The catacombs were a barometer of social stability, their decay mapping periods of peace and times of conflict when honoring the dead became a dangerous or neglected practice. Even the sarcophagi themselves were designed as diagnostic instruments. Master craftsmen in various ancient cultures developed complex sealing mechanisms using mortars, resins, and stone plugs that were engineered to last for specific durations. The material choices were a language. A sarcophagus made of a certain grade of limestone would erode at a known rate, while the resins used to seal its lid would crystallize and crack in a distinct sequence over centuries. If a culture maintained a vibrant, continuous memory of its ancestors, these containers would be maintained, their seals repaired, and their surfaces cleaned. But if that cultural memory was broken, the sarcophagus would be left to the elements. Its deterioration would then follow the predicted timeline, the state of its seals and surfaces telling a clear story to any future discoverer about how long the individual within had been actively remembered. The object became a clock measuring the lifespan of legacy. This funerary engineering represents one of humanity's most profound meditations on mortality. These builders understood that how a society treats its dead is the ultimate reflection of its beliefs about life, legacy, and its own continuity. They did not build for a single funeral, but for the entire lifespan of a culture, creating structures that would document the rise and fall of remembrance itself. The enduring presence of these ancient resting places testifies to a deep-seated belief that death is not an end, but a bridge to future understanding, and that the most lasting monuments are those that encode the fragile, beautiful human desire to be remembered. This same sophisticated understanding of long-term communication would soon be applied to the living, as engineers began to design systems to manage the flow of information across entire empires. Their communication networks were designed to think. Ancient engineers built systems that did more than transmit messages. They modeled the flow of information itself, creating prophetic instruments that measured the health of a civilization's collective mind. The Inca quipu system transformed knotted chords into a complex data storage language. Each knot's position, type, and the color of its string held specific meaning, recording everything from census data to sacred histories. The true genius of this system was its built-in fragility. The specific types of fibers used and the complex knotting techniques required constant, specialized maintenance. If the administrative state became bloated and inefficient, or if the master knot makers failed to pass on their knowledge, the system would decay in a predictable sequence. Colors would fade in a particular order, and delicate knots would loosen or unravel, leaving gaps in the recorded narrative. The quipu chords were not just records, they were living diagnostics, their physical deterioration mapping the loss of cultural memory and bureaucratic coherence in real time. This same foresight was engineered into the vast signal tower networks of ancient China. These towers, stretching across mountains and plains, were not placed at random intervals. Their sightlines were calculated with geometric precision, creating a chain of visibility that allowed messages to cross vast distances in a single day using fire, smoke, or flags. The system was a physical model of information speed. It was engineered to function optimally only under a stable, centralized authority that could maintain the towers and staff them with trained operators. When political control weakened or priorities shifted, the network would fail diagnostically. The collapse would begin at the empire's outer edges, where towers were most vulnerable to neglect. One fallen tower would create a blind spot, forcing messages onto slower, more arduous routes. The pattern of these failures created a visible map of the empire's disintegrating attention, a prophecy written in silent, abandoned watchtowers. The impulse to engineer information flow appears even in the earliest written records. In ancient Mesopotamia, the clay tablet accounting systems used by temple scribes employed strict formatting conventions and complex sealing methods. The specific layout of columns for recording grain, livestock, and labor was a cognitive technology designed to process economic data with maximum efficiency. The system itself contained a prophecy about bureaucratic evolution. As an administration grew more complex and burdened by its own records, the formatting would begin to break down. Tablets would become crammed with information, seals would be applied with less care, and the standardized script would devolve into hurried, personal shorthand. The degradation of the tablet's form was a direct reflection of the system's strain, a clear signal that the administrative machine was becoming overloaded and losing its coherence. This understanding of optimal flow shaped even the movement of human messengers. The Persian Empire's legendary royal road featured a network of way stations and supply depots spaced at distances that reflected a profound calculation. It was not merely the distance a horse and rider could travel in a day, but the optimal rate for information to move without becoming distorted or outdated. The engineers were modeling the metabolism of an empire. If the empire expanded beyond its ability to maintain this network, or if internal conflict disrupted the steady rhythm of riders, the system would falter in a telling way. Messengers would arrive with stale information, or way stations would run out of fresh horses, creating delays that followed a predictable geographic pattern. The breakdown of the messenger service was an early warning system, signaling that the empire's body was growing too large for its nervous system to effectively manage. These communication engineers viewed information as the lifeblood of civilization. They understood that its free and accurate flow was as critical as water for agriculture or stone for fortifications. They did not just build channels for words, they built calibrated instruments that would measure the vitality of their society's connections. The silent quipu, the abandoned signal tower, and the overcrowded clay tablet all stand as enduring testimonies to this insight. They were built to document their own obsolescence, to show future generations the precise moment when a culture's ability to talk to itself began to fail. This sophisticated awareness of systemic health extended beyond the flow of information, reaching into the very places designed to heal the human body. Their healing spaces were designed to feel the pulse of public health. Ancient medical engineers constructed hospitals and temples that functioned as diagnostic instruments, their very architecture encoding predictions about the relationship between societal stability and collective wellness. The Asclepiae of ancient Greece, dedicated to the god of healing, were not simply places of prayer. They were carefully sited near sacred springs and built with specific porticos and sleeping chambers oriented to capture healthy breezes and sunlight. The entire complex was a calibrated environment, engineered to foster recovery through a balance of clean air, pure water, and psychological tranquility. This delicate balance, however, was the system's prophetic core. The healing process within an Asclepieion was designed to work optimally only when the surrounding environment remained unpolluted and the social order was calm enough to support the meticulous rituals of care. If the nearby springs became contaminated from upstream settlement, or if social conflict disrupted the supply of dedicated priests and attendants, the temple's therapeutic effectiveness would diminish in a measurable way. The architecture itself contained a silent forecast, predicting that public health would inevitably falter when the natural and social harmony supporting it began to decay. Roman military engineers applied this same foresight to their valetudinaria, the earliest known field hospitals. These facilities were masterclasses in pragmatic design, featuring advanced water systems for sanitation and sophisticated ventilation to prevent the spread of illness among wounded soldiers. The engineers who designed them, however, built in subtle failure points. The gradient of the water channels, for instance, was calculated to flush away waste efficiently only if maintained to a specific standard. The ventilation shafts were positioned to create cross breezes that would only circulate fresh air if the surrounding camp followed strict hygiene protocols. When the empire became overstretched and maintenance standards slipped, these systems would fail in a diagnostic sequence. The water channels would clog at predictable points, and the airflow would stagnate in certain wards first, creating pockets where disease could spread rapidly. This was not a random tragedy. It was a physical manifestation of a system under stress, a clear signal that the logistical and disciplinary backbone of the army, and by extension the empire itself, was weakening. The hospital's decline was an early warning written in stone and mortar. This medical foresight reached a profound level of sophistication in the ancient Ayurvedic hospitals of India. These institutions were designed according to precise principles that linked architecture to wellness. Specific building materials were chosen for their natural properties, with certain types of clay and wood believed to promote healing and maintain a pure atmosphere. The spatial arrangement of patient wards, herb gardens, and treatment rooms followed a sacred geometry intended to harmonize with the human body and the natural world. The system was a holistic model of health. The engineers understood that the hospital's own physical decay would tell a story. If the knowledge of Ayurvedic principles was diluted over time, or if environmental changes made the traditional building materials ineffective, the facility would deteriorate in a recognizable pattern. The specific clay plasters might crumble in a distinct way, or the medicinal gardens would fail to thrive, signaling a disconnect between the built environment and the medical philosophy it was meant to embody. The building's health was a direct reflection of the vitality of the knowledge it contained. Long before the concept of germ theory, ancient civilizations engineered sophisticated quarantine facilities that also served as prophetic monitors. From leprosaria in medieval Europe to isolation compounds in the ancient Near East, these structures featured separate water sources, dedicated waste disposal, and airlock-style chambers. The engineering was a physical algorithm for containing contagion. These systems were designed to function perfectly only with vigilant administration and a clear understanding of the protocols. When population density increased beyond a sustainable point, or when periods of famine and social chaos eroded the resources needed for strict isolation, the quarantine mechanisms would break down in a predictable fashion. The separate water supply might be compromised first, or the isolation barriers would be breached out of necessity. The failure of the quarantine was a stark physical indicator that the community was undergoing a stress so severe it could no longer protect its own members from internal threats. These medical engineers viewed public health not as an isolated concern, but as the ultimate measure of a civilization's resilience. They built their healing spaces to be both shelters and sentinels, designed to document the fragile, enduring relationship between human well-being and the world we inhabit. This same profound understanding of legacy would soon be applied to the institutions designed to shape the human mind itself. Their schools were engineered to think across centuries. Ancient educational architects designed learning spaces not just to house knowledge, but to actively model and predict its transmission, embedding physical markers that would signal shifts in a society's intellectual vitality. The great academies of ancient Greece were laid out according to a precise geometry of inquiry. The spatial relationship between the open-air lecture hall, the scroll-lined library, and the shaded groves for discussion was a physical algorithm for intellectual growth. This layout functioned optimally only during periods of vibrant philosophical exchange and open debate. The system contained a silent prophecy. If cultural priorities shifted toward dogma, or if social pressures restricted free discourse, the architectural harmony would break down in a measurable way. The groves might be neglected first, their paths overgrown, signaling a decline in spontaneous dialogue. The library might be physically separated from the lecture hall by new walls, its access restricted. The decay of this engineered relationship provided a clear, physical diagnosis of a culture closing its own mind. This predictive genius was woven into the very walls of medieval Islamic madrasas. These institutions were marvels of integrated design, with courtyards for reflection, libraries for preservation, and student quarters for communal living. The architects used specific materials and techniques that served as long-term gauges. The intricate tilework on a courtyard wall, for example, was not merely decorative. Its complex geometric patterns required master artisans to maintain. If educational funding was diverted or intellectual freedom waned, the maintenance of these tiles would be one of the first casualties. The patterns would begin to fade or sections would fall away, their deterioration creating a visible timeline of declining institutional support and artistic expression. The building itself was a barometer, its beauty directly tied to the health of the scholarship it housed. In ancient China, the sprawling imperial examination halls were engineered as vast machines for meritocratic selection, but they also contained a profound prediction about their own integrity. The individual examination cells were designed with specific sightlines and acoustic properties meant to ensure absolute fairness and prevent cheating. The system was calibrated to function only under a stable, impartial administration. If governmental corruption increased or if the examination system itself became politicized, the hall's engineered features would fail in a diagnostic sequence. The surveillance corridors might be blocked off, or the acoustic buffers between cells would be compromised, allowing whispers to pass. This physical breakdown was not accidental. It was a built-in signal, a stone and wood testament to the erosion of meritocratic principles, showing future observers the precise moment when the system's ideals no longer matched its practice. Across the world, in the scriptoria of medieval European monasteries, a different kind of educational prophecy was being inscribed by candlelight. These copying rooms were engineered for perfection, with precisely angled windows to maximize daylight and specialized desks to support the long, meticulous work of manuscript reproduction. The specific lighting conditions and workspace ergonomics were a calibrated system for producing flawless texts. This system contained its own quality control. If the monastic order faced economic hardship or intellectual decline, the standards of production would slip. The carefully maintained window fittings might be neglected, casting imperfect light on the parchment. The specialized desks might be replaced with cruder furniture, leading to a detectable change in the scribe's handwriting and an increase in errors. The degradation in the quality of the manuscripts was a direct reflection of the declining conditions in the scriptorium, a slow-motion message about the fading of a literary tradition. These educational engineers possessed a unified understanding that the spaces where we learn are not passive containers. They are active participants in the process of thought itself. They built their academies, madrasas, examination halls, and scriptoria as living systems, designed to thrive during periods of intellectual ferment and to document their own decline when those conditions faded. The enduring stones of these institutions challenge us to consider what our own schools and universities will say about our priorities to those who study their ruins centuries from now. This same sophisticated understanding of societal patterns was engineered into the bustling heart of every ancient city, the marketplace. The stones of the marketplace were their economic crystal ball. Ancient engineers understood that commerce was not just an exchange of goods, it was a pulse, and they designed the very spaces of trade to measure its every beat. The Greek agora was far more than an open square. It was a precisely engineered social machine. Its spatial arrangement, with specific areas designated for different goods and a central platform for civic announcements, created a delicate balance. This layout fostered optimal interaction and price transparency, but it functioned perfectly only during periods of economic diversity and fair competition. The engineers built in silent prophecies. If trade became monopolized by a few powerful interests, the designated zones would be disrupted. Stalls would cluster unnaturally, blocking the free flow of people and information. The architecture itself would begin to feel strained and congested, its intended harmony broken. This was a physical diagnosis of an economy losing its competitive vitality, a warning written in the organization of daily life. Roman engineers embedded similar foresight into their bustling forums. The specific paving stones, the gradient of the drainage channels beneath the market stalls, even the height of the curbs, were all calculated for a specific volume of commercial activity. This system was a marvel of urban efficiency, but it was also a calibrated gauge. When economic vitality waned, the failure was not random. The drainage channels, designed for a certain amount of waste from food and goods, would begin to silt up first in the less frequented sections of the forum. The wear patterns on the specific stones leading to the money changers tables would become uneven, showing a decline in financial transactions. The forum's physical decay mapped the empire's commercial health with startling accuracy, its stones recording a story of prosperity and decline. Along the sprawling Silk Road, this predictive engineering took on a global scale. The caravanserais, those vital way stations in the desert, were built with storage rooms of precise dimensions and security systems of clever complexity. Their design was a direct reflection of the trade they supported. The storage capacity was calculated for typical caravan sizes, and the security features, like intricate locking mechanisms on strong rooms, were engineered to deter specific, known threats. The system contained its own diagnostic sequence. A sustained drop in trade volume would manifest physically, with storage rooms remaining empty and their doors weathering in a distinct pattern from lack of use. If political instability introduced new forms of banditry, the existing security would fail in a recognizable way, showing where new weaknesses had been exploited. The silent, decaying caravanserai was not just a ruin. It was a data point in a vast stone-built network model of global exchange. In the great port cities of the ancient world, warehouse engineering reached a prophetic peak. The sophisticated granaries of Ostia and the storage complexes of Alexandria were designed with specific ventilation systems to preserve grain and complex inventory management features like marked floor tiles and standardized storage jars. These were not just practical solutions, they were physical algorithms for economic stability. The ventilation systems were calibrated for a specific throughput of goods. If economic specialization increased, leading to a reliance on a single type of imported grain, the preservation system would be stressed in a new, measurable way. If resource scarcity struck, the inventory system would show the strain, with marks on the tiles indicating increasingly frantic attempts to manage dwindling supplies. The degradation of these warehouse features provided a clear, archaeological record of an economy under pressure, its vulnerabilities etched into the very floors where merchants once walked. This collective vision across diverse cultures and continents reveals a stunning unity of thought. From the Greek agora to the Roman forum, from the Silk Road outpost to the bustling port warehouse, ancient engineers were not merely building structures for commerce. They were creating permanent observers, stone and mortar sentinels designed to document the immutable laws of economic flow. They understood that wealth, trade, and resources move in currents as predictable as the seasons, and they had the genius to build instruments that could measure these currents for centuries to come. Their work stands as a timeless testament, a challenge to see our own economic landscapes not as chaotic markets, but as systems whose patterns were understood long ago. This integrated vision represents their ultimate engineering achievement. They did not see a city as separate from its fields, nor its temples as isolated from the stars. The entire civilization was viewed as a single, breathing organism, and they engineered its every part to monitor its collective health. The Maya provide a perfect illustration, their existence a seamless loop of observation and application. The precise movements of Venus, tracked from the Caracol Observatory, dictated the timing of their planting seasons. This celestial schedule then determined the necessary capacity of their Cholton water reservoirs, which in turn influenced the maximum sustainable population their cities could support. A shift in the stars would eventually ripple through the entire system, from the heavens down to the last underground cistern, a chain reaction of cause and effect they meticulously built into their world. The Roman mind operated with the same holistic logic, just expressed through different means. Their legendary road network was the empire's circulatory system, but its health was dependent on the aqueducts that fed the communities along its path. The gradients of those aqueducts were calculated in relation to the road's foundation, and both were designed to fail in a specific sequence if maintenance faltered. A crumbling road in a distant province was never just a local problem. It was a single blinking light on a vast civilizational dashboard, signaling that the entire logistical network was under strain. Their engineering created a unified language of warning where a silted harbor, a degraded coin, and a stressed aqueduct were all telling the same story from different vantage points. The sheer sophistication of this approach is what modern systems theorists are only now beginning to fully comprehend. These ancient engineers were not just building things. They were building relationships, creating physical models of how their societies actually functioned. They understood the fundamental principle that we now call systems thinking, that everything is connected. A flaw in the metal of a sword was connected to the stability of a distant mine. The fading echo in a ball court was connected to the strength of community bonds. The precise alignment of a pyramid was connected to the slow, grand wobble of the planet itself. They encoded this understanding into the most durable materials they could master, creating a permanent operating manual for civilization, written not in words but in stone, water, and celestial alignments. This integrated prophetic system stands as humanity's most profound attempt to leave a message for the future. They were not predicting a single doom, but mapping the recurring patterns of growth, stability, and transformation that all complex societies experience. Their work offers a timeless insight that our greatest challenges are rarely sudden surprises. They are the culmination of long-term trends, trends that these master builders learn to measure and inscribe into the very fabric of their world. As we navigate our own era of profound change, their ancient dashboard of civilization invites us to look at our world with the same interconnected vision, to see the subtle signals before they become crises, and to remember that the most enduring wisdom is often written in the language of the land, the sky, and the stones. They built an entire civilization as a single prophetic instrument, a unified system of stone, water, and sky designed to measure the health of a society across centuries. Our journey through their world reveals a stunning reality. These master builders were not merely constructing monuments. They were creating sophisticated prophetic systems, encoding urgent warnings about civilizational cycles and transformational thresholds directly into the landscape of daily life. They saw their cities not as permanent achievements, but as living entities with predictable rhythms of growth, stability, and renewal. The astronomical alignments of their megalithic temples were not just for ceremony. They were the hands on a cosmic clock, tracking ages so vast we can barely comprehend them. The deliberate failure points in their aqueducts and roadways were not flaws, but diagnostic features, physical algorithms predicting the precise moment when resource consumption would outpace sustainable supply. Their integrated genius spanned every aspect of existence, from the sacred geometry of a temple floor to the specific weave of a textile, creating a comprehensive early warning system for societal health. This was not magic. It was a profound form of applied science, a deep understanding of cause and effect played out on a civilizational scale. They calculated time not in years, but in the slow precession of stars and the gradual accumulation of silt in a harbor. They understood materials not just for their strength, but for how they would erode, patina, or resonate over millennia, each change a letter in a message to the future. The sheer sophistication of their temporal calculations and their holistic systems thinking continues to challenge our modern assumptions about ancient capabilities. We often view the past as a simpler time, but their vision was in many ways more expansive than our own. They planned for time frames that stretch beyond our typical political or economic cycles. As we face our own era of rapid change and environmental uncertainty, their legacy offers profound lessons. They teach us about sustainability not as a modern buzzword, but as a practical engineering principle. They demonstrate resilience not as mere survival, but as the intelligent design of systems that can absorb shock and recover balance. Most importantly, they remind us of the critical need for a long-term perspective, for building and governing with an eye toward the seventh generation, and the seventh generation beyond that. The messages they painstakingly encoded in stone, water, and celestial alignments continue to speak to us across the great expanse of time. They offer a timeless insight. Our greatest challenges are rarely sudden surprises. They are the culmination of long-term trends, patterns that these ancient observers learned to measure and inscribe into the world. Their work suggests that the most profound prophecies are not about predicting a fixed and inevitable future. They are about understanding the deep patterns that shape our possibilities, giving us the wisdom to recognize the turning points in our own age. What might we learn if we applied their interconnected vision to the challenges we face today? How would our cities, our economies, and our relationship with the natural world change if we began to build for the next 1,000 years instead of the next 10? I invite you to reflect on how these ancient wisdom traditions might inform our path forward. Share your thoughts in the comments below. If this exploration into humanity's enduring quest to understand time and destiny has sparked your curiosity, please subscribe for more journeys into the world's great historical mysteries. Remember, the future is not a distant shore we are powerless to reach. It is a pattern, and the ancients left us the